Alternating series and absolute convergence. Alternating series. Let b sub k be a sequence of positive numbers. Then a series of the form the sum of minus 1 to the k times b sub k, or the sum of minus 1 to the k minus 1 times b sub k, is called an alternating series. So essentially an alternating series is a series whose terms alternate in sign. For example, the sum as k goes from 1 to infinity of minus 1 to the k minus 1 divided by k, which equals 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 and so on, is an alternating series. In fact, notice that without the alternating signs, this would be the divergent harmonic series. So let's call this the alternating harmonic series. Now let's think about the partial sums of this series. The first partial sum, S1, is equal to 1. Then to obtain the second partial sum, we subtract 1/2 to obtain S2 equal to 1/2. Then we add 1/3 to obtain S3 equal to 5/6. Then we subtract 1/4 to get S4, add 1/5 to get S5, subtract 1/6 to get S6, and so on. So notice that the partial sums seem to be hopping back and forth about some particular number and getting closer and closer to that number. That would be the limit of the sequence of partial sums, or the sum of the series. To be a little more careful about this analysis, let's notice that the partial sums with odd indices are a decreasing sequence. S1 is greater than S3, S3 is greater than S5, and so on. Also, the partial sums with even indices form an increasing sequence. So the sequence of partial sums with odd indices, as well as the sequence of partial sums with even indices, are monotonic bounded sequences, and so must converge. Also, the differences between successive partial sums, that is, the terms of the series itself, approach 0, and so therefore these sequences approach the same limit, and that limit will be the sum of the series. Theorem on convergence of alternating series. Let the sum of a sub k be an alternating series if 1. The limit as k goes to infinity of the absolute value of a sub k is equal to 0, and 2. The absolute value of a sub k plus 1 is less than the absolute value of a sub k for all sufficiently large k, then the series converges. Notice that the second condition says that the sequence absolute value of a sub k is an eventually decreasing sequence. For example, let's consider the series, the sum from k equals 0 to infinity of minus 1 to the k divided by 2k plus 1. Let's first notice that the limit as k goes to infinity of the absolute values of the terms, the limit as k goes to infinity of 1 over 2k plus 1, is clearly equal to 0. Now let's look at the absolute value of the k plus first term. That's 1 over 2 times k plus 1, which equals 1 over 2k plus 3. Now that's clearly less than 1 over 2k plus 1, which is the absolute value of a sub k, and that's true for all k. So we conclude that the series converges because of these two facts. Example. Show that the sum from k equals 1 to infinity of minus 1 to the k times k divided by k squared plus 10 converges. We need to show that the two hypotheses in the previous theorem are true for this series. First, it's clear that the limit as k goes to infinity of k over k squared plus 10 equals 0. In other words, the absolute value of the kth term approaches 0 as k goes to infinity. Next, we need to show that the absolute values of the terms are an eventually decreasing sequence. In other words, we want to show that the absolute value of a sub k plus 1, which is k plus 1 divided by k plus 1 squared plus 10, is less than the absolute value of the kth term, which is k over k squared plus 10, for all k greater than or equal to some number. To do this, we can use a little bit of calculus. Let's let f of x equal x divided by x squared plus 10. Then f prime of x, using the quotient rule, has the denominator x squared plus 10 quantity squared, and the numerator is 1 times x squared plus 10 minus x times the derivative of the bottom, which is 2x. That simplifies to 10 minus x squared divided by x squared plus 10 squared, which is clearly less than 0 for all x greater than the square root of 10. So the function f is decreasing for all x greater than the square root of 10. Since the square root of 10 is between 3 and 4, we can conclude that f of k plus 1 is less than f of k for all k greater than or equal to 4. That is, the absolute value of a sub k plus 1 is less than the absolute value of a sub k for all k greater than or equal to 4. So the absolute values of the terms in our series form an eventually decreasing sequence. Therefore, the series converges by the preceding theorem. Now let's look at an example showing that condition 2 in the previous theorem is necessary. The following is a divergent alternating series whose terms approach 0. 1 minus 1 plus 1/2 minus 1/2 squared plus 1/3 minus 1/3 squared plus 1/4 minus 1/4 squared, and so on. Notice how the series is constructed. All of the negative terms comprise the sum of minus 1 over k squared, which we know is a convergent p-series. But the positive terms, 1 plus 1/2 plus 1/3 and so on, are the terms of the divergent harmonic series. Since the sum of the negative terms is finite, while the sum of the positive terms is infinite, the series itself must diverge. But the first hypothesis of the preceding theorem is satisfied, that is, the limit as k goes to infinity of the absolute value of a sub k is equal to 0. However, the second hypothesis of the theorem is not satisfied, because beginning with the third term, plus 1/2, each positive term is greater than the absolute value of the preceding negative term. Therefore, the absolute values of the terms did not form an eventually decreasing sequence. Now let's be a little bit more careful about arguing that the series diverges. Let's suppose that n is even. Then the partial sum s sub n equals 1 minus 1 plus 1/2 minus 1/2 squared and so on up to 1 over n over 2 minus 1 over n over 2 squared. Since this partial sum is a finite sum, we're free to rearrange the terms, so let's group the positive terms together and the negative terms together and factor a minus 1 from the negative terms. The second group of terms here is a partial sum of the sum from k equals 1 to infinity of 1 over k squared, which converges. And in fact, the partial sum is less than the infinite sum, so minus that group of terms is greater than minus the sum of 1 over k squared, which is a finite number. On the other hand, the first group of terms is a partial sum of the divergent harmonic series, and so that group of terms tends to infinity as n goes to infinity. And so s sub n approaches infinity as well. Estimating the remainder. Recall that the nth remainder of a convergent series, the sum of a sub k, is the difference between the sum of the series and its nth partial sum. Capital R sub n equals the sum of a sub k minus s sub n, which equals the sum from k equals n plus 1 to infinity of a sub k, since s sub n is the sum from k equals the starting index up to n of a sub k. We have the following estimate on the absolute value of the remainder for a convergent alternating series. If the sum of a sub k is an alternating series and the limit as k goes to infinity of the absolute value of a sub k is equal to 0, and the absolute value of a sub k plus 1 is less than the absolute value of a sub k for all k greater than or equal to capital N, then the absolute value of the remainder R sub n is less than the absolute value of a sub n plus 1 for all n greater than or equal to capital N. Notice that the upper bound on the absolute value of R sub n here is simply the absolute value of the first term in R sub n, or in other words, the absolute value of the next term that's not included in the partial sum s sub n. Also notice that the hypotheses here are exactly the same as those of the theorem on the convergence of an alternating series. Now let's think about why this is true. Imagine a partial sum s sub n, to which we add the next term a sub n plus 1, to obtain the partial sum s sub n plus 1. The limit of the partial sums, that is the sum of the series, will be somewhere between s sub n and s sub n plus 1. The distance from s sub n to the limit is exactly the absolute value of r sub n, and the distance between s sub n and s sub n plus 1 is exactly the absolute value of a sub n plus 1. Therefore, this picture makes it clear that the absolute value of r sub n is always less than the absolute value of a sub n plus 1, provided that we're far enough out in the series that the absolute values of the terms are decreasing. Example. Estimate the difference between the sum from k equals 1 to infinity of minus 1 to the k minus 1 divided by k and its 100th partial sum, 1 minus 1/2 plus 1/3 minus 1/4 up to plus 1 over 99 minus 1 over 100, which happens to be approximately 0.6882. We need only estimate the 100th remainder. The absolute value of r sub 100 is less than the absolute value of the 101st term, which is equal to 1 over 101, which is approximately 0.00991. Now let's remark that from this estimate we can conclude that the sum of the series is between the partial sum 0.6882 plus and minus the estimate on the remainder 0.00991. Those two numbers are 0.6783 and 0.6987. Example. Find n so that the nth partial sum of the sum from k equals 0 to infinity of minus 1 to the k divided by k factorial is within 10 to the minus 5 of the sum of the series. Then compute that partial sum. Here we want to find n so that the absolute value of the nth remainder, which is less than the absolute value of the n plus first term, is less than or equal to 10 to the minus 5. The absolute value of the n plus first term is 1 over n plus 1 factorial, and so we want to solve the inequality 1 over n plus 1 factorial less than or equal to 10 to the minus 5. That's equivalent to n plus 1 factorial greater than or equal to 10 to the 5th. Now, computation shows that 8 factorial is 40,320 and 9 factorial is 362,880. So 9 factorial is the smallest factorial that's greater than or equal to 10 to the 5th. So we want n plus 1 equal to 9, which gives us n equal to 8. Now let's compute the 8th partial sum. The sum from k equals 0 to 8 of minus 1 to the k over k factorial equals 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial and so forth up to plus 1 over 8 factorial. That's equal to 1 over 1 minus 1 over 1 plus 1/2 minus 1/6 plus 1 over 24 and so on up to the last term 1 over 8 factorial, which is 1 over 40,320. If we do the arithmetic exactly, we get the reduced fraction 2,119 divided by 5,760, which is approximately 0.367882, a number that is guaranteed to be within 10 to the minus 5 of the exact sum of the series. Example. An alternating series can converge extremely slowly. For instance, the sum from k equals 2 to infinity of minus 1 to the k divided by the natural log of k converges since the limit as k goes to infinity of 1 over the natural log of k equals 0 and 1 over the natural log of k is decreasing for all k greater than or equal to 2. But if we compute an estimate on the 1/1,000,000th remainder, we find that the absolute value of that remainder is less than 1 over the natural log of 1,000,001, which is approximately 0.072, which is not a particularly small number. We can add up 1,000,000 terms of this series, and that partial sum is guaranteed to be only within 0.072 of the sum of the full series. The absolute value of r sub 10 to the 12th is less than 1 over the natural log of 10 to the 12th plus 1, and that's approximately 0.036. And in order for the absolute value of r sub n to be less than, say, 0.01, we need to have the natural log of n plus 1 greater than 100, which is equivalent to n plus 1 greater than e to the 100th power, which is roughly 3 times 10 to the 43rd power. Now, convergence is so slow here because the terms of the series approach zero very slowly, so slowly that the sum of the absolute values of the terms diverges. In other words, it's only the alternating nature of the series that allows it to converge. Absolute convergence. A series, the sum of a sub k, is said to converge absolutely if the sum of the absolute value of a sub k converges. It turns out that every absolutely convergent series converges. That is, if the sum of the absolute value of a sub k converges, then the sum of a sub k converges. For example, the sum of minus 1 to the k divided by k squared converges absolutely because the sum of 1 over k squared converges. So this is an alternating series that converges by the alternating convergence theorem, yet the corresponding series whose terms do not alternate in sign also converges. Conditional convergence. If the sum of a sub k converges while the sum of the absolute value of a sub k diverges, we say that the sum of a sub k converges conditionally. So any convergent series converges either absolutely or conditionally. For example, the sum of minus 1 to the k divided by k, which converges by the alternating series convergence theorem, converges conditionally because the sum of the absolute values of the terms is the harmonic series which diverges. Alternating p-series. If p is greater than 1, then the sum of minus 1 to the k divided by k to the p converges absolutely because the sum of 1 over k to the p converges. On the other hand, if p is greater than 0 and less than or equal to 1, then the sum of minus 1 to the k over k to the p converges conditionally because the sum of 1 over k to the p diverges. Geometric series. The sum of the absolute value of x to the k converges if x is strictly between minus 1 and 1 and diverges otherwise. Therefore, the sum of x to the k and the sum of minus 1 to the k times x to the k converge absolutely whenever they converge. The ratio and root tests. By applying the ratio or root test to the sum of the absolute value of a sub k, we can determine whether or not the sum of a sub k diverges or converges absolutely, provided the test doesn't fail. Here's the ratio test. Suppose that the absolute value of a sub k plus 1 divided by a sub k approaches a limit rho as k goes to infinity. Then the sum of a sub k converges absolutely if rho is less than 1 and diverges if rho is greater than 1. If rho equals 1, the test fails. And here's what the root test says. Suppose that the kth root of the absolute value of a sub k approaches a limit rho as k goes to infinity. Then the sum of a sub k converges absolutely if rho is less than 1 and diverges if rho is greater than 1. If rho equals 1, the test fails. Example. For what values of x does the sum of x to the k divided by k, a, converge absolutely, b, converge conditionally, and c, diverge? We'll use the ratio test. Here, the absolute value of the k plus first term divided by the kth term is equal to the absolute value of x to the k plus 1 over k plus 1 divided by x to the k over k. That's equal to k over k plus 1 times the absolute value of x to the first power. Since k over k plus 1 approaches 1 as k goes to infinity, this approaches the absolute value of x as k goes to infinity. So the series converges absolutely if the absolute value of x is less than 1 and diverges if the absolute value of x is greater than 1. If the absolute value of x equals 1, that is, if x equals plus or minus 1, then the ratio test fails. So we need to consider x equal to plus and minus 1 separately. If x equals 1, the series is the sum of 1 over k, which is the divergent harmonic series. If x equals minus 1, the series is the sum of minus 1 to the k over k, which converges conditionally. So the series converges absolutely if the absolute value of x is less than 1, converges conditionally if x is equal to minus 1, and diverges if x is less than minus 1 or greater than or equal to 1. Why absolute convergence matters. Rearrangements. Example. Consider the sum from k equals 0 to infinity of minus 1 to the k over 2 to the k, which equals 1 minus 1 over 2 plus 1 over 2 squared minus 1 over 2 cubed, and so on. Since this is a simple geometric series, the sum from k equals 0 to infinity of minus 1/2 to the kth power, we can compute the sum of the series easily using the formula 1 over 1 minus minus 1/2, which is 1 over 3/2 or 2/3. One possible rearrangement of this series is the series in which we add 1 plus 1 over 2 squared and then subtract 1 over 2 to the first power, and then add 1 over 2 to the fourth plus 1 over 2 to the sixth before subtracting 1 over 2 cubed, and so on. Essentially, we're just adding two positive terms before backtracking to add the next negative term. Notice that this rearrangement is a series with exactly the same terms. So the question here is whether or not this rearrangement actually sums to the same value of 2/3. Here's another example. The sum from k equals 1 to infinity of minus 1 to the k minus 1 over k equals 1 minus 1/2 plus 1/3 minus 1/4, and so on. In a later section, we'll learn that this series sums up to exactly the natural log of 2. If we rearrange this series in the same way as the previous one, we have 1 plus 1/3 minus 1/2 plus 1/5 plus 1/7 minus 1/4 plus 1/9 plus 1/11 minus 1/6, and so on. And the question is whether or not this rearrangement sums up to the same value, the natural log of 2. It turns out that this rearrangement does in fact sum to a different number, the natural log of 2 times root 2. So it is possible to rearrange a convergent infinite series and get a different sum. We have the following theorem on rearrangements of series. 1. If the sum of a sub k converges absolutely, then every rearrangement of that series also converges absolutely to the same sum. Note that this tells us that the rearrangement in the first example above does in fact sum to 2/3. Part 2 of our theorem says something rather remarkable. If the sum of a sub k converges conditionally, then for any number s, there is a rearrangement of that series that converges to the number s. In other words, given any conditionally convergent series, it's possible to rearrange the series so that it sums to any number we like. To illustrate the second part of the preceding theorem, let's take the sum from k equals 1 to infinity of minus 1 to the k minus 1 over k, which sums to the natural log of 2, and rearrange it so that it sums to 2. We do this by first adding just enough positive terms until we get a sum that's greater than 2. It turns out that 1 plus 1/3 plus 1/5 and so on up to 1/15 is roughly 2.022. Now let's call this Q1. Next we backtrack and add the first negative term, which brings our total back below 2. Let's call that Q2, and it's approximately 1.522. Next we add positive terms beginning at 1 over 17 until we get a total that's greater than 2 again. That happens when we add 1 over 41, which gives us a total of roughly 2.004, which we call Q3. Next we backtrack and add a negative term to bring the total back down below 2. That gives us roughly 1.75, which we call Q4. Next we add positive terms again until we get a total that's greater than 2, and then backtrack and add a negative term to bring the total back down below 2. And we just continue this process. The infinite sum that we're constructing is in fact a rearrangement of the original series because it eventually contains every term in the series, and in fact the partial sums of this rearrangement converge to the number 2. And using more or less the same general procedure, we could rearrange the terms of this series so that they sum to any number whatsoever.